Welcome. Today we'll be shifting our study from the tangent line to the area under a graph. But before we do that, we need to review sigma notation. So the goal of this video will be to determine a sum written in sigma notation and also to write a sum using sigma notation. It is often important to be able to find the sum of the first n terms of a sequence. That is, find the sum of a finite number of terms. Rather than write down all of these terms every time, we use a summation notation as a more concise way to express this sum. So we can rewrite this sum using what's called sigma notation. This symbol here, the Greek letter sigma, which is an S in our alphabet, is an instruction to sum or add up the terms. The integer I is called the index of the sum, and this tells us where to start the sum and where to stop the sum. So essentially you can think of this as an adding machine. Let's take a look at how this works. I think of the index I as like the counter. The counter will start at 1 and it will go to 4, and after 4 it will stop. So essentially we're going to be adding 4 terms, and this 3 to the power of I is our formula. So what we're going to have here is first I is equal to 1, so we'll have 3 to the first power, plus now I is going to be a 2, 3 to the second. Next I will be a 3, 3 to the third. And the last value I takes on is the value of 4, so we'd have plus 3 to the fourth. So we have this formula that generates terms, and the sigma notation tells us that we're going to find the sum of the terms. So now we just have to add these up. 3 to the first is 3, 9, 27, and 81. So the sum would be 120. Let's try another. Again, here's our formula. Here's our index. Now we're using the variable k. It doesn't matter now. It normally starts at 1, but it can start at any value. It always increases by 1, and it will stop after the value of 4. So the first value of k here would be 0. We have 0 squared plus 2 plus the k value is going to take on the value of 1, 2, 3, 4, and then stop. So again, notice the value of k went from 0 to 1, 2, 3, 4, and then it stopped. And now we need to evaluate each of these and then find the sum. 1 squared plus 2, 2 squared plus 2, 3 squared plus 2, and 4 squared plus 2. And we find the sum, which is equal to 41. Okay, let's take a look at one more. Again, the formula will change, the variable for the index may change, but the procedure stays the same. So the first value of I is equal to 1. Next value is 2. Next value for I is 3. And the last value for I is equal to 4. Notice the index is I. And the value of I changes from 1 to 2 to 3 and then to 4. So we have to find the sum. Now this would be a lot of work to do by hand. Let me show you on the graphing calculator how you can also evaluate something written in sigma notation. The way we do this is we hit second stat for our list options, go over to math, so right arrow twice, select option 5 for sum. Now we have to go back to our list menu, so second stat for list, and now we right arrow once over to ops and select option 5 for sequence. What we want to do is sum a sequence. So now we type in our formula, which is 1 divided by 2i, but I'm going to type in 2x instead of 2i because it's more convenient, comma our variable x, comma where the index starts, which is 1, and where it ends, which is 4. Close the parenthesis for sequence, and also close the parenthesis for sum. Hit enter, It's going to give us a decimal approximation, but remember, if we hit math, enter, enter, it will convert this back to a fraction for us, 25/24. So the calculator can be a big time saver for a problem like this. Okay, the next skill we want to review is if we have a sum, can we write this using sigma notation? Now this is kind of like a little puzzle that we want to figure out the pattern. What I'm talking about here is we know we're going to have a counter, and using that counter we want to be able to generate a formula that will generate these terms. So if we take a look at this, we could write 3 as 1 times 3. We could write 6 as 2 times 3. 9 is 3 times 3. 12 is 4 times 3. And of course 15 is 5 times 3. And what we see here is the pattern of 1, 2, 3, 4, 5. So that would be our index. So we could rewrite this as the summation from I equals 1 to 5, and our formula would be 3 times I in each case. Again, we can check this, but we can see from our work here that it matches perfectly. When I is equal to 1, we'd have 3 times 1, or 3. When I is equal to 2, 3 times 2 is 6, and so on. And they're not all quite this straightforward. For example, when we take a look at this problem, we do see a pattern. Here we're adding 3, here we're adding 5, and we're adding 7. But that doesn't really help us come up with the formula. This one is a little bit more challenging in that all of these terms are one larger than a perfect square. What I mean by that is 2 can be written as 1 squared plus 1. 5 can be written as 2 squared plus 1. 10 would be 3 squared plus 1. 4 squared plus 1, and so on. Again, we should recognize the pattern that we have in 1, 2, 3, 4. We could use that value as our index. So we can rewrite this as the summation using I equal to 1 to some value. We'll figure out that in a minute. But our formula would be I squared plus 1. Now to figure out the ending value of the index, we simply have to just count the terms. 1, 2, 3, 4, 5, 6. If I goes from 1 to 6, we'd have 6 terms generated by this formula. And let's just check the last term. When I is equal to 6, we'd have 6 squared plus 1, or 37. And so our formula generates the correct terms, and this notation tells us that we have a sum. I hope that helps review sigma notation. Thank you for watching.